Okay, guys, now I'm afraid in quantum field theory, there's always a lot of details that you have to keep in your mind. So it's very easy to get lost. So what I want to do is I just want to start off today by reminding us of what we're trying to do. So the quantity we're calculating Z of J is the quantity at the top of the slide. It's a path integral d phi e to the I s of phi. And then we've added in this term integral d4x j of x phi of x. Now, why is this quantity interesting? It's interesting because of the red box. We said by taking functional derivatives with respect to j, and then setting j is equal to 0, we get the path integral, which is an integral d phi, e to the is, and then we've got this product of the fields, phi of x1 up to phi of xn. And our claim was that this quantity makes contact with our previous operator quantization, because this particular path integral is equal to the time-ordered correlation function of the fields x1 up to xn. And we know how to calculate that time-ordered correlation function. So that's what makes Z of j an interesting quantity. If we can calculate Z of j and work out these derivatives, set j is equal to 0, we can compare it to what we obtained using operators, and this will really be our demonstration that the path integral is completely equivalent to what we did with operators. So at this point, what we've been trying to do, we've been trying to calculate Z of j. Now, how did we do that? Well, we studied a one-dimensional integral, and we learned how to do the integral. Basically, by shifting, it looked very much like a Gaussian integral, and then we could actually perform the integral. So we repeated that same logic for the path integral. And the shift of the integration variable that we had to perform was that phi of x is equal to phi naught of x plus phi primed of x. In this shift, phi naught of x is a constant, meaning it's a function that does not depend on phi of x. So it's a constant as far as the integration variable goes. We're integrating over all fields phi of x, and whatever fields you're integrating over, phi naught of x stays the same. And it's in that sense that phi naught of x is a constant. Then when we work out Z of j, this is an integral d phi prime e to the I s of phi prime, and then we've got this extra 1/2 integral d4x j of x phi naught of x. And if you remember, there was a little bit of work in showing that that exponential becomes this form. Now, because j of x and phi naught of x are completely independent of phi primed, we can take them out of the path integral. And then the integral d phi prime e to the I s of phi prime is simply equal to 1. So we got our answer for Z of j as e to the 1/2 integral d4x j of x phi naught of x. Good. Then we said, well, we have to solve for phi naught of x. To solve for phi naught of x, we need to solve the middle equation in the green box. So d mu plus m squared acting on phi naught of x was equal to minus I j of x. How did we solve that equation? We solved it using the Green's function method. So the first equation in the green box defines the green function, and then the solution for phi naught of x is given by the last equation in the green box. Plugging that solution for phi naught of x into our expression for Z of j, we get the expression in the blue box. Z of j is the exponential of 1/2 integral d4x integral d4y j of x g of x comma y j of y. In this blue box expression, the only unknown that there is g of x comma y, the Green's function. And we're going to have to solve for the Green's function. Now, you may look at this expression and say, hang on, we don't know g of x and y, but we also don't know j of x and j of y. Well, that's true. We don't know j, but we don't need to know j. You see, how do we use j? We're always taking derivatives with respect to j and then evaluating things at j is equal to 0. So we never need to know what j of x is. We just take derivatives with respect to j of x and then set j is equal to 0. So really, in the blue box, the only unknown is g of x comma y. So we should calculate that Green's function, and we will calculate it. We'll calculate it soon. But before we do that, I just would like to use this answer to work out what is this time-ordered correlation function. So I want to take some derivatives with respect to j of x. I want to set j as equal to 0, and we'll work out the time-ordered correlation functions in terms of the Green's function. And after that, we will calculate the Green's function. Good. Okay, I'm going to use a fact. I'm just going to use it now, but we'll prove it later. And the fact that I'm going to want to use below, so please remember this, g of x comma y is actually equal to the g of y comma x. So this function is symmetric. And I'm not asking you to accept it. I'm telling you we will prove this later. Okay? In fact, after we've calculated g of x comma y, you'll see that manifestly it's symmetric under swapping x and y. So that'll be something that is absolutely clear. So the first simplest thing that we could calculate is the time-ordered correlation function of two fields, phi of x1, phi of x2. Remember, the time-ordered correlation function of a single field vanishes, so that's trivial. So this is the first non-trivial case that we can consider. And what is this given by? Well, we should take a functional derivative with respect to j1. We should also take a functional derivative with respect to j2. That should act on z of j, and then we should evaluate that at j is equal to 0. So this is what I want to do now. Let's see, what do we get? So we'll have delta j of x1. And now let's calculate the functional derivative with respect to j2 of that expression in the blue box. Now, you've done computations like this before, and I think that what you know is when you act on that exponential, it'll bring the exponent down, and we'll multiply by the exponential again. So the exponent will come down. We'll have a 1/2. We will have an integral d4x, an integral d4y, and now we need to take the functional derivative of that exponent. Well, the first thing that we can do is delta j of x2 can hit j of x, and that'll give us a 4-dimensional delta of x minus x2 multiplied by g of x and y, j of y, plus, then we can also hit the j of y. There's two sources there. We can hit both of them. When we hit the second source, well, we'll do nothing to j of x, so j of x stays here. We get g of x comma y, and now we need to hit the j of y. And this will give us a delta 4 of y minus x2. So that's what we get by differentiating the exponent. And then we need to again multiply by the exponential. So let me space this out a little bit so that we don't get a formula that looks too cluttered. We'll have e to the 1/2. And now I don't want to call my integration variables and my exponent x and y again, because I don't want to mix them up with this xy integral that we've got down the bottom here. So let me call this dx prime dy prime, just so I don't mix up my integration variables, and I can call my integration variable anything that I want. And I'll get g of x prime, j of x primed, g of x primed comma y primed, and then j of y primed. That's the exponential, and then I will close the square brackets. And then after I've taken both derivatives, I have to evaluate things at j is equal to 0. Good. One more derivative to calculate. Now, when we take this next derivative with respect to j of x1, where can we act? Well, okay, so let's see. We can act anywhere where there is a j, okay? So we could act over here. If we act here, this j of y is going to turn into a delta function. And if we act here, the j of x is going to turn into a delta function. So acting with that derivative, we're going to remove the two j's that I've underlined in red, and we'll get something completely independent of j. So when we plug in j is equal to 0, we will actually get a non-zero result. The other thing that you may be tempted to do, you might say, well, let me take the derivative with respect to j sitting over here or j sitting over there. If you do hit those two j's, you'll bring down the exponent again, and the two j's that I've underlined in red will still be where they are. And that means when you set j is equal to 0, you'll get a vanishing result. So I claim if you hit these green j's, you get 0. And if you hit the red j's, you get something that's non-zero. Okay. What I want you to do now is I want you to calculate that second derivative. And then I want you to set j is equal to 0. When we come back at the start of the next recording, we'll be doing exactly that calculation. So if you do it right now, if you take the derivative with respect to j1 and set j is equal to 0, you'll be able to check if you know what you're doing by comparing to the result that I get.